I'm going to be starting part 2 of the vintage workbench. The next piece of equipment that I'm going to work on is this EICO Model 147 signal tracer. And where I'm going to be starting is trying to solve a few safety issues. One of the safety issues is this plug that is on the unit. It came with all of that tape you see on the right connected or wrapped over those connections, and you'll notice that the connections are not even soldered, they're just wrapped. This is of course not really good practice. So what I'm going to be doing is cleaning all that up and doing it the way that I consider to be the right way, which is soldering the connections so you don't get sparks, and then of course covering everything with an appropriate shrink wrap tubing package. What we'll do is we'll solder these in a different way. We'll use what's called a Western Union splice instead of this pigtail, and then we'll be putting shrink wrap over the connections, each of those, and then we're going to be putting a large piece of shrink wrap over the whole thing. So I'll get a little of that done and we'll come back to that. Then we're going to go inside the unit and we're going to remove any capacitors that are across the AC line. For now we'll just go without the capacitors, and then later if we find that there is any kind of noise on the AC line, we'll put some safety capacitors back in to suppress that. But the thing you don't want to do is leave the paper capacitors in these units. So let me get to the next step and I'll show you that when I get there. I'm going to try now to show you how a Western Union splice is made. This is a splice that was used by the people putting the telegraph together in the early West by Western Union. That's why it's called a Western Union splice. What you do is you start out with the wires stripped like this. You put them you leave a little space at each end, and then you start wrapping one wire at one end like that, and the other wire goes the opposite direction at the other end. The reason that the splice was done this way is not only does it give you an area that causes the wires to be contiguous, but also the people who put the early Western Union system together saw that this was a stronger splice. It's less likely to pull apart, particularly if in those days they used stranded wire, a solid wire. But once this is soldered, it's a very, very strong splice. So that's a Western Union splice. I'll do this other one and then we'll solder them up, and then we'll pull some of this shrink wrap. You'll notice that you have to be sure you put the shrink wrap on before you do the soldering. Otherwise, you can't get it on. So I've put red in the underside to insulate the two wires from each other. And then I'm going to slip this larger piece down over the whole thing and shrink it to produce a cover for the whole thing. So it'll basically be, when I finish, double insulated. Now I've soldered the connections. I'll slide this red shrink wrap down, and then the larger, and shrink it, and then the larger one over the whole arrangement and shrink that with heat. And there are the inner shrink wrap tubing in place. I'll shrink those now to make them a little tighter. And now we'll slide the larger shrink wrap the larger tubing over. And here's the finished product. The next thing we're going to do is go inside and check to see if there are still any paper capacitors across the AC line. What I'm particularly interested in removing are capacitors like this one that is shown between one side of the AC line and ground. These were put in to reduce the noise coming in on the AC line. And in the 40s and into the 50s, AC lines were often very noisy because there was little, if any, filtering, and if you lived anywhere near a site that used motors, there was a lot of sparking and other things that generated a lot of noise on the line. Today, most power lines are much better conditioned, so I'm not really worried that I need that capacitor, and it's a safety hazard because if it ever shorts, it will cause a fire inside the unit that could, because it's across the AC line, could go unnoticed and spread elsewhere. So generally it's a good idea to replace these capacitors. So for now though, I'm just going to clip this one out if it's still in there. This is the underside of the chassis, and the capacitor that I'm looking to remove is this one right here. So the first thing that I'm going to do is just clip this lead. I'll trim it up later. That's partly so that I can get to this other lead on the other side of the capacitor, which is right in there. And you see I've removed that capacitor. Now what I'm going to go in and trim up those leads so that they're not sticking out. But if I need it later, I'll replace this with a good safety capacitor. But for right now, I'm just going to leave it out. Now what I'm going to do is I'm going to spray some deoxit down here in the power switch and work it back and forth a little bit to make sure that it's as clean as possible. I generally like to clean the power switches with some kind of cleaner. Deoxit's a pretty good one. And no, I'm not part of the deoxit challenge. I'm not trying to, I don't take money for this, for what I do, nor is this an advertisement for deoxit. It's just, that happens to be one of the products that I use. So I'll be spraying it down here, and then I'll be working this switch back and forth until I see that most of that corrosion, which I've taken some of it off with a pencil eraser, and the rest I'm going to now take off with deoxit. And by the way, you can use other products here. In fact, there's a much cheaper product that I buy at Walmart for electrical cleaning that I often use. I'm not going to use it in this place mainly because it's out in the garage and the deoxit's in here. So we'll get that cleaned up, and then we'll be ready to start maybe doing some testing on this unit. Now I've brought a tube tester in. This is a Lafayette tube tester. It's a model 99-5063. It's from the period. I actually own 3 of these. This is a newer one than the one I originally owned. I first bought my very first tube tester, which is the predecessor of this Lafayette model, in, I believe, 1959. And I still have it. It still works fine. I decided to bring this one partly because it's in a little better condition. The other one's a little scratched up, but also just because it was the closest one I could find when I went and checked. This is just an emission tester, and if you watched my series on the SX62, you know that that's generally all I really use these for, except in cases where I'm trying to match tubes, where I'll use one of the B&K testers or the Hickok 600A. But you don't really need those expensive tube testers, and in all candor, you don't even really need a little cheap tester like this one. You can test the tubes in the circuits just as well, and if not better, than you can ever test them in a tube tester. But what I'm going to use this for is just to verify that all the tubes' filaments are intact, that they do produce a reasonable amount of emission, and that way, before I try a power-up, I'll be assured that I don't have any shorts in the tubes and that all of the tubes will at least light up and produce electrons. Here is the 6SQ7, which is the tube that's used in the very input right here. I've written the tube numbers above them. For some reason, EICO left the tube numbers off in the original schematic, so I've written them in there. And you'll notice that the 6SQ7 basically consists of a triode and a pair of diode plates. Normally these are used for automatic volume control and AM detection in a radio, but here they're using the diodes in the wattmeter circuit, which we may talk about later. So there's basically 3 tests on this tube. The first test is on the triode, and the next 2 tests are on the 2 diode plates. So let's see how those read. This is the triode section, and it's pin 2. The diode, and as you see, it reads good. The diode sections, you have to set the load to 100, and that's 4. And notice that we're just right on the top of the replace and into the questionable area. And on number 5, the other diode, we're in the middle of the questionable. So we may have some trouble with this tube in the wattmeter circuit. We'll see later whether that's true or not. But we do know that 3 things are true. 1, the tube doesn't have any shorts. I've already tested for that. 2, the filament is good. And 3, there is emission from the tube, and it does flow to the triode and to the 2 diode plates. So I'm going to finish testing tubes on this unit, and just to be sure that they're not dead, and then we'll be going for a power-up. This is a good opportunity to illustrate something that I've mentioned in other videos, but in case people are watching this one and didn't watch the others and aren't aware of this, what I'm going to be doing is there's a capacitor down here. It's a 20 microfarad, 450 volt electrolytic, and I've unsoldered the, it has a resistor that used to go here, and then a red lead that used to go over here to the rectifier tube. So I've disconnected everything from the capacitor. So we're going to be testing it, but it's going to be out of circuit. And I'm going to show you the peak Atlas Esr Meter. We'll hit test, and you see it will analyze, and then it says that the capacitor has no ESR and is a 16.76 microfarad capacitor. Now, let me set up the Sencore and measure the same thing. Now I have the Sencore LC102 connected. You'll see it up here. And I hope you'll be able to read the readings. Let's see if I can get a better picture there. You can see on the right that it's set to 300 volts right here. And we're going to check first the capacitor value. And it reads 14.6 microfarads. But now we're going to check capacitor leakage at just 300 volts. Now remember, this is supposed to have about 330 volts on it normally, and the capacitor is rated for 450. We're reading 19 milliamps. That's definitely a leaky capacitor. Now, let's go up to the voltage that it's going to actually be operating at. It's around 350 volts. Almost 20 milliamps. So what we're demonstrating is that while these ESR meters are very useful for low voltage capacitors in transistor circuits and similar sorts of things, when it comes to equipment like this that operate in the several hundred volt range, you really do need a capacitor tester that will test leakage at those higher voltages. So I think I'm going to have to replace that capacitor. In fact, I'm sure of it. There are other sections that are actually worse than this section. But at any rate, I think what I'm going to do in this case is actually restuff the capacitor. But I'll make that decision after I've got it open. I've taken the top off of this electrolytic because I'm going to be replacing everything inside it. And you'll notice that it's sawed off. I used a hacksaw to saw across. This allows me to clean out everything there as well as what's in here. This is tar, by the way, and a heat gun is helpful in melting the tar so you can get a lot of that out of there. You don't need to get all of it out because it's not conductive, but depends on how much of a neatnik you are as to whether you want to go further than I am. I'm not a real neatnik, so if it doesn't show from the outside, I'm not too concerned about a little tar. At any rate, what I'm going to be doing is, when I'm done, is putting this back on, and then I'll be wrapping it with muffler tape. It's that aluminum tape you can buy at the auto parts store to repair mufflers. And when you're done, it looks almost like a vintage unit or a mint unit. But at any rate, I'm going to replace those 4 capacitors, and this project is turning out to be a little more than I had expected. I had hoped that it might work right out of the bag, but it's drawing way too much current because those electrolytics are really out of spec. So I'll be replacing electrolytics, checking and maybe replacing some paper capacitors, and when I get to that point, I'll fire it up one last time and then go through a checkout of the functions. But I'm trying to wrap this video up in no more than another 3 or 4 minutes so that I can get on to the next piece of equipment, and I kind of like to stick to a 20-minute total, or 25 minutes. So anyway, I'll see you on the next video segment. I've finished installing the 4 capacitors. I'll show you on the schematic in a second. But I wanted to show you first what it's done not only for the voltage. I now have the 260 volts that, once again, I'll show you on the schematic where you're supposed to have that. But the big improvement, or another big improvement, is on the current draw. Earlier, with the leaky capacitors in the circuit, at 100 volts of input, I was drawing about 0.6 amps. In other words, about 600 or 650 milliamps. Now I'm drawing, well, around 0.3. In other words, about half as much current from the AC line. And the reason is that, of course, those capacitors were overloading the transformer and everything else. Now let me show you the schematic where the voltage is that I'm interested in. If you see right there, I'll turn the paper so that it's easier to read, where it says 260 volts. That's what I'm reading on the meter now. So I'm getting the proper voltage on the out of the power supply. So now what I'm going to do is button everything up, or at least put the lid back on that those new capacitors, and tape that up, and then I'll be able to test out the functions of this unit. Well, here it is turned on, but not back in its case yet. And it's drawing about 0.35 amps at 117 volts of input. And I have a probe connected to the RF input, and I have the control set to RF, because that's one of the main purposes of this, is to be able to monitor RF. Now, the probe that I'm actually using is a probe that I rebuilt. Originally, this was on a night vacuum tube voltmeter, but I rebuilt it to be an RF detector probe. And so let me show you. Now, all you're going to hear is just 60 cycle, because that's predominantly what there is right here. But I'm going to touch the probe tip, and as you'll see, the signal tracer picks up the signal. And now what I'm going to do is home in on that eye tube. It's a little bit weak, but we're going to see if we can drive that eye tube you can see the eye tube closing up as we apply signal. Maybe a little closer here. So the signal tracer parts of this all work. I am not going to bother checking the watt meter. These were notoriously bad watt meters. There are much better ways to measure wattage, including that kilovolt unit that I showed earlier in this series. But at any rate, this has been the restoration of the Model 147 EICO signal tracer. I'm now going to put it into its case and take it back to the garage and pick up the next unit in the series, which will have to wait until part 3. And that is the resistor capacitor bridge that's also made by EICO. So look forward to part 3. In the meantime, have a nice day.